Hello, everyone. Welcome to our talk about customizing confidential VM deployments in Azure. My name is Swamy, and I have Chris with me, who is co-presenting along with me. So just a bit of intro about ourselves. So I've been with Microsoft for a really long time. So currently working as engineering manager in Azure Confidential Computing. Previously, I worked as security researcher in Microsoft Security Response Center. So I like all things security, particularly interested in security mitigations and hardening space. Probably it makes sense for some of you, like why I'm in confidential computing area today. Right? Chris is relatively new to Microsoft. Soon he'll be celebrating his first year anniversary with us. He is in the same team and same org as I am. And he too comes from security background. He worked as security developer at US government previously. From what I've seen him, he is really awesome. So the topics that we'll be covering today is some background about our talk and specific deployment of confidential VM in Azure, referred as a direct and export, which allow more customization option, and then some demos. So we have made a deal with the demo gods today to help us make sure that our demos goes fine. So we'll see that. You'll find our talk interesting if you've been toying with SGX previously and looking to explore confidential VM to get similar properties, or if you are exploring confidential VM in general to see how you can lift and shift your application with much greater control, or in general, like if you're in confidential computing space, you want to know where it's heading, what kind of things are happening, so you'll find our talk interesting. There are a few concepts and terminologies that will come up in our talk. We might cover them briefly, so just putting out some of the links there for any future reference. And we don't have ton of time today, so we can't really get into really deep to any of them. So just have 30 minutes. I might have already consumed 5% or so of that. Let's move quickly. To start with some relevant background, right? In the previous OC3 edition, the last year, a couple of my colleagues made this presentation about idea of exploring open source software for guest firmware needs within the confidential virtual machine space, right? Specifically for the in-guest system firmware. We are happy to say that since then we have made good progress on that idea and making it available in some form or the other within Azure for our customers to explore it further. So our talk today is going to demonstrate how that exploration has become real thing in some capacity. Right? Just a quick note, right? The confidential VMs have been generally made available in Azure since the last summer. This is more of a managed deployment. So it offers much stronger isolation for the virtual machines from the hosting environment. You have seen a talk about this from Microsoft, Jin, and then Caroline earlier. So you might have got a good idea about it. And it is built on top of AMD's EPIC 3 processor that offers SEV-SNP technology. And this is clubbed with disk encryption features to offer stronger isolation story. Everything is rooted to AMD's root of trust here. Right. So our main topic of today is on how to customize these confidential VMs in Azure. Right. So building on top of what confidential VMs already offers, we want to provide more options for users to control and customize their confidential VM deployments. So what do we mean by customization here? So it's basically providing users options to customize different components that make up the confidential VM's TCB or trusted computing base. In the context of guest partition of a confidential VM or in general for any VM, you can think about there are three major components, right? There is the system's firmware, guest operating system, and the application or the workload in itself, right? So when we think about system firmware, so what kind of customization or options we can give to users? So basically leveraging an open source and allowing them to control this component is a good sort of customization there. And when you think about guest OS, like these are operating system file, modules, and a lot of things are there, and there could be secrets in some scenarios and all, right? So having giving option for users to bring in their own protection, like integrity, encryption, or both, or whatever ways you can implement those protection, right? And even the same thing will get extended to application you can do alongside the OS, or it can be done independently, right? And all this customization needs to be done in an environment that user trust, right? So it could be their own on-premise system or a trusted environment running inside another TEE, right? So we want to basically give full control for users to manage their TCB according to their security and confidentiality needs, or for their whatever is needed for their posture, right? And you can't really think about confidential computing without really getting into the attestation. So attestation is another component where you want users to have more control, more flexibility. So this is what we are trying to achieve with customization here. And so it's natural that some of you will think, like, why do we need all this customization apart from the fact that one size fits all? The primary reason is to take full control of the trusted computing base here, right? So what are the benefits of it, right? As I was alluding to some of them in the previous slide, right? Users can precisely control what makes up their TCB and when to manage, when to update them, and what to bring in and how to audit and all. Right? And they can leverage open source for different components where they can get full transparency. So specifically for the in-guest system firmware, which is very critical. And then they can use their own attestation stack or service. And in the previous session, like previous to previous session, under the Project Amber thing, right? So they're talking about all these things right there. Um, and all of this benefit comes with some cost, right? So you can't really get away from them, right? So the more the control you get, the more the responsibility one has to take here. So some of the costs that we can think about is, like, you may have to do additional work of managing the guest TCP components on your own versus something that's get managed by someone else in a streamlined manner, right? And some features may not be available or can't be offered due to the implementation choices. Like if you use a specific thing for your system firmware, and if it can't offer a functionality that you're looking for, so then either you have to develop that or you need to wait or move on to a different one, right? And since there are some different experiences, right, in terms of, oh, you have to build something and then bring it in, so you're actually basically changing that experience, and then it will also impact how the workflows will get executed, and there could be some challenges with how you diagnose or debug the issues when it happens. So there are certain things that you have to pay. It's all about convenience versus control, and then what's the degree of trust. All those things play in here, right? And there can be many different possible set of custom deployment options. So the thing that mainly differentiates between the deployment is how the in-guest system firmware is implemented. So one such simple implementation that we are currently exploring is referred as direct Linux boot, where Linux kernel is directly used for the in-guest system firmware. So let's understand this bit more, but please be aware that there can be multiple implementations here, and we might enable more and more as we go further into the future. So, so some important concept related to Azure Confidential VM that I should mention before proceeding is about VMGS disk. So, if you have attended the talk earlier in the day from Carolina and Engine, you might have got some idea about what the VMGS disk is all about, right? So, the VMGS stands for Virtual Machine Guest State. VMGS is the initial state from which the guest starts. You can think about this as the initial memory state from which the VM bootstraps, right? The state is measured by the hardware, in this case, AMD security processor. So during the VM launch, so this measurement is referred as launch measurement or launch digest, which is available as part of hardware report for attestation once the VM boots. And even the AMD security processor enforces these things, right? So user attest the launch measurement to make sure that the VM started from the exact state they wanted it to be, and they created it. So this can be done. So for direct Linux boot deployment, as we are going to use Linux kernel and the initrd as the initial state to begin with, so that means the Linux kernel and the initrd will become the initial state for the confidential VM to start with. So the reason we are referring in this slide the Linux kernel as enlightened Linux kernel is to indicate that it needs latest SNP enlightenments to communicate to the hardware via the SEV device to fetch the attestation report and other enlightenments that are needed to work on the SEV-SNP device. Right? So for the customer, for this custom deployment option, so the way the VMGS disk is enabled today is via user able to build the VMGS disk using the open source tooling, and then choosing the Azure supported enlightened Linux kernel and initrd by this to put inside their VMGS disk for the initial said, some of the tools are on the path of getting open source, but everything will be based off open sourcing tool. Right? So the measurement of the Linux kernel and initrd is available for users to attest later when the VM launches. That's, as I mentioned, it's part of launch digest. It's the launch digest, a launch measurement here. And then there is a disk for user to package and protect their workloads. If you compare this with any normal OS disk, so there'll be partition to hold kernel, which is not used in this deployment, right? So because the kernel that is placed in the VMGS disk is the one that's always active, and that is going to stay as long as the VM exists. It won't load any other kernel, so that's the kernel that will be active. So then there is root partition. So the workloads are packaged into a partition that is that can be invoked after doing a change root, or you can totally do away with the root partition and have an app partition, package all the dependencies and all. You'll see some of these things in the demo. And in our schema, we also have another partition called metadata partition. So where we have an archive that collects a lot of things which can be measured collectively and later attest during the launch, right? So some of the things that we put in this archive are the config files that capture some of the security properties, and there is user in it, so that brings the customization, SSH key, and many other things can be part of this archive. So let's understand how a simple boot flow looks like here, right? So when the VM comes up, right? So as the hardware brings up this partition, the SNP partition, the first thing that runs is the initrd. Initrd starts executing from the guest state that was prepared earlier. So this, as I mentioned earlier, the guest state, the initial guest state is captured and measured by the hardware, and it's also available for users to attest it, right? And then the user init executes, which is part of the metadata partition, which is kept in the archive. So the initrd will basically knows the measurement, and then it will go and unwrap and get to the user init and executes to do more custom boot to customize the boot flow further. Right? Once it is done, and then the workload can be invoked in many ways. The user init can orchestrate invoking the workload. It can do root to the root partition and run the application from there, or it can have a archive. It can look into an archive where the application has all the dependencies and all, and you can run there, or you can have a SSH session open and then interact with the guest remotely, right? So there can be this can be implemented in multiple ways. This can be customized, the whole boot flow, everything as a user wanted for that scenario. So okay, so let's look at how the trust flow, right? Even when the things are getting prepared and how the VMs are getting provisioned. So so the goal, so we will be looking at what a typical flow looks like when the artifacts are getting prepared for the deployment. So the goal of the preparation steps is to do all the customization that are needed for the deployment and capture the measurements that can be attested when the VM boots up in the cloud environment, right? That's the goal here, right? The one of the first step would be to prepare the disk to include the packages, the workload packages, and all the dependencies, everything, right? So once that is done, so need to protect the disk and capture the configuration that you want to attest and look forward later on when it is getting deployed. And the configuration, you can think about in case of if you're doing an integrity protected partition, the configuration could be the root hash, the hash key, all those artifacts that are needed for the later, right? So, and depending upon your scenario, it can be many other things and all. So you have the root hash for the measurements, and then once the as I was talking about metadata partition, there will be an archive. So this archive is going to store this config, user init, and all the other security properties, and you can get the digest of this archive, like archive hash, to be used later, right? And then there is initial get state where Linux kernel and initrd is getting used, and we know, as I was talking about, this is the launch measurement, launch digest that can be used to attest later when the VM boots up, right? And then there is there's a key thing here, right? There is concept of identity block, ID block in the AMD's ABI stack. Right? So this ID block is a place where there are certain fields that are captured, and it can be signed by the user, and the public key of that signer is available for user to attest later on. So this ID block can contain some of the information which is provided by the Hyper-V to the SNP firmware, and it will be available for the user within the guest to attest it. So in our case, we are going to leverage some of the fields in the ID block, like family ID and image ID, and to store the hash of the archive which is placed in the metadata partition. So this is the one that links the disk with the VMGS disk with the OS disk partition. So, and it also helps in doing a measured boot or step-by-step attesting the boot sequence and then getting to the application. Moving on to the next slide. So this is where you're provisioning the prepared image in the cloud environment. So now a user has all the information to attest the deployment. Let's look at how it worked back with when the confidential VM is launched in the cloud environment. Right? So hardware loads and measures the initial state, so which is going to be init in the kernel, and then the init script executes there, and then it gets the from the ID block, it can get the digest, and it can get the from that it can get the hash of the archive, so it knows it's going to talk to a write archive. So then it does all the basic stuff. It go and mount the partition, it gets the archive, extract the archive, and then it will reach out to the user in it, so which will further customize the boot as needed, as a user want it to be customized. So it can do validation of integrity or other settings, and then it can do a root or get to the application directly. And once the application gets executed, so the first thing it's going to do is get the hardware report and perform the attestation by talking to any of the KMS solution they want. So at this point in the report, it has all the feeds, all the values that we captured in the previous step, and everything can be attested to make sure that the whole VM has been launched with the exact state, with exact parameters and exact things that the user has provisioned for. So after this, so I'm done with my session, and Chris is going to show us some of these things in action. Yeah.
All right. Thanks, Swamy. So I'm going to step through a sequence of demos. So 3 demos in total. The first being like a full OS deployment where the root partition of the OS, say in Ubuntu OS, is integrity protected. In this demo, we'll integrity protect the reference OS disk and then deploy it into Azure with protect, then prepare the VMGS disk, then deploy to Azure, and then launch the OS. Then we'll show in the second demo how to deploy a self-contained application to be run at launch, say a single binary that just needs to run like a web server in this case. So since in this case there is no OS to integrity protect, the application will just be packaged into the metadata archive as it is. And then we'll conclude with an extension of the last demo by packaging and running a container. One thing to notice is that the only parts that steps that differ are the first and the last step of each of the demos. All right, let's step through what conceptually we're going to do in this demo first. So on the right, you see that we'll have an OS disk as a reference. So first thing that we do for this reference OS disk that has no user is we have to specialize it to provide it a user so that it boots with a user that we can SSH into. So we specialize the disk, then we protect the specialized disk and create the archive for with the protection artifacts. In this demo, we'll show a reference to the integrity protection of, again, the root partition with DM integrity. Then we'll create the firmware disk using the measurements of the archive from the last step. And those will be hashed by our tooling, then loaded into the image ID and family ID. Then we'll create the confidential VM. Then on boot, the initRD will verify the archive in the disk against the values in the identity blocks, image ID and family ID, as you can see. Then it'll extract the archive. It'll then set up the integrity protected file system and then root into the guest OS. All right, let's see how this looks in practice. So again, for the OS, we first need to specialize it to provide a user. C, we'll give it with the specialized command. We'll give it a reference OS, as you see above. We also have to provide a host name, then a username, and as well as an SSH key. This will output into this disk.phd. It's important to notice that this actually takes place in the user's development environment, which does not need to be a SEV-SNP device. The only step that needs to, and also the only step that needs to be online is actually the last step, so the CVM creation. All right, so now that we've actually created, specialized the disk, we can integrity protect it with DM Verity. So let's do this next. Okay, so first this shrinks the root file system of the OS to be as minimal as possible. Then it shrinks the root partition. It then computes the hash tree and the root hash for DM Verity. Then it creates a read-write partition for use after boost as a scratchpad. Then the hash tree and the disk metadata are loaded into an archive, which is then added into a new metadata partition on the disk itself. And as you can see, this is the root hash that's printed out onto the screen. Again, I want to say that integrity is, reference integrity protection that we offer. So next, we actually create the disk for the ingest firmware. So first, we have to link the OS disks and the firmware's disk by including the hash of the archive, as we just see. We also include the initRD and the kernel that make up the ingest firmware. All right. Now, finally, we create the confidential VM by providing the disks that we created in the previous two steps, as well as relevant deployment information, such as the VM name itself. So under the hood, this will create a resource group. It'll upload the OS disk and firmware disks, and then finally, it'll create the deployment specific templates. So again, this is the only online step of the deployment. And then also, interestingly, the OS disk and the firmware disk can be priorly uploaded in case you want to reuse the disks. Right, so now that the confidential VM is deployed, we'd like to assert that the firmware deployed is the firmware that we created in our development environment. So on the top panel, you'll see our development environment with the prepared firmware disk. So we can dump the identity block of the firmware to see the family ID, image ID, and the launch measurements. And then in the bottom panel, we'll fetch an attestation report that's been printed into a human readable format. And we can verify that the fields agree. So now we can see that the family ID is equivalent to the family ID in the prepared image, as well as the image ID. And finally, we can see that the launch measurement is also agrees with the launch measurement. All right. Now let's move on to the second demo. So again, this is a self-contained application. So imagine that we have an empty disk on the right. So first we have to load the application itself and an entry point script onto the disk. So then once we have this application on the disk, we create the firmware disk using the measurements from the archive that was where the application resides. Then we create the confidential VM, and the remaining steps are pretty equivalent. On the boot, the initRD will verify the archive and the disk against the values in the ID block. It'll then extract the archive, then it'll launch the application. Let's see how this looks in practice now. So here you can see like an application archive where we have the web server and our entry point script, which we call the order file. We'll inspect the order file next just to show exactly how minimal this can be to actually start up your own static binary. Here you can see that all we do is we just start the web server and then park a shell to run indefinitely. So now that we have our application directory, to package the application, we simply provide the application directory that we just saw as the custom init to the OS disk protection set. We use the protection type of custom because there's no full integrity OS to protect. We also provide the application directory as the custom in this case. This will just load it onto the archive that's then loaded into the metadata partition of the disk. All right. The remaining two steps are equivalent to in the full OS, where we create the firmware disk based on the application archive that we just prepared. and then we can create the CVM itself. So now that the application is deployed, we can actually navigate to the web server to actually see it serve up that attestation report with the different report fields. So here you'll see that we can actually fetch the image ID, family ID, and the launch measurement itself. Yep. All right. Time. Now, in this final demo, I'll try to go through this quickly. So this is more of an extension of the last demo, where instead of a minimally stripped down static binary, say we have a container that has, say you have an application that has dependencies and you want to package that into a container. Again, imagine we have a blank disk. The first thing, again, to do is to load the container with the artifacts into the archive on the disk, create the firmware disk using the measurements from the archive, create the confidential VM. On boot, the initRD will verify the archive with the ID block. It'll then extract the archive. It'll then launch the container. Let's see what this extension looks like. So again, this is more just to show the flexibility of this deployment type, where you can modify the order file so that it can actually pull up a container itself. So in this case, we extend this by deploying a container workload by modifying the application directory to include a Docker image, the Docker binaries, static binaries, and we modify the order file, which we'll then investigate next. So here you can see that all we have to add is that we have to unpackage the static Docker binaries that we've fixed ourselves, mount a street group file system, start the Docker daemon. It'll then load the Docker image. It'll start the container itself, and then it'll park a shell. All right. Similar to in the application, the prior demo that we saw, we again provide the directory for the container as the custom init here with the custom protection type. And again, this just packages the container directory into an archive that isn't loaded onto the metadata partition. And again, the remaining two steps are equivalent across. And so because of that, I'm going to skip to verifying that the container that we created is actually being run. So you can see the family ID, image ID, and the launch measurements from the firmware file that we prepared. And on the right, we'll see the running container in the confidential VM. So you can see that the launch measurement on the right is equivalent to the launch measurement on the left. All right.
Yeah, that's kind of getting into our presentation. There are a bunch of references. If folks want to know more about other things that we are talking about or referring during the talk, right? And yeah, I think if you're interested in exploring or shaping this further, there's a sign-up form. You can reach out to us, and also there is a email ID here, so you can reach out to us if you want to know more or if you're interested in exploring this further.